Hi, everyone. In this video, I'm going to just briefly describe Newton's three laws and the idea of force, and then we'll do an example of applying Newton's second law with particular forces. So let me go ahead and first of all, just introduce you to Newton's laws. Probably a lot of you have seen this maybe at some point in the past, but the goal here, we're going to go into chapters 5 and 6 of the textbook. And we'll first of all introduce the laws and then consistently use them and apply them to different forces, different situations in chapters 5 and 6. So for today, I just want to first of all introduce or talk about what the laws say. So Newton's laws, let's just talk about the first law, which you've probably heard stated before. For example, you probably heard an object at rest tends to stay at rest, or an object in motion tends to stay in motion. What I mean by that, now that we know the definitions of acceleration, velocity, right? To stay in motion means stay at a constant velocity, right? An object at rest tends to stay at rest means its velocity tends to stay zero. Another way of saying that is an object will not accelerate, or it tends to not accelerate, but we know we can create accelerations. So how do we do that? Well, let's say an object will not accelerate, unless a force is applied to it. And I'm going to say a net force is applied to it. So basically what this means is that you have to push the object, right? There has to be a force pushing or pulling. And we kind of think or have a feeling for what a force is, right? It's a push or a pull. There are forces that are contact forces. So you push on a table, you're actually in direct contact. There are non-contact forces like gravity. Gravity is a force that will accelerate a ball, even though two objects are not actually in contact with each other. In either case, they are a force. So this new quantity force has to be present to cause something to change its velocity or accelerate. Now, what do I mean by net force? Net force means there has to be a resultant force that is not zero, right? So you can have more than one force. And since forces are vectors, they have a magnitude and a direction, it is possible for them to add up to zero. So for example, a skydiver, as they fall, they have a force due to gravity pulling down, but they also have an air resistance force pointing upward. And if they get going fast enough, those two forces are equal and opposite to one another, and they will cancel each other out or add up to zero. So I would say the net force in that case is zero. Now the skydiver just doesn't stop in midair. They keep falling, but they fall at a constant velocity, right? Because now their acceleration is zero. There are many situations that the Newton's first law applies to, which you probably see in everyday life, right? If you're a passenger in a car and the driver slams on the brake, you tend to keep going forward. One of the tricky things about this in history has been that our experience is that things actually eventually stop. Right? If I slide something across the ground, it will come to a stop. But the reason for that is that there's a frictional force. And if you kind of imagine, right, that there's no friction, maybe you imagine, first of all, going out onto a frozen lake, an ice-covered lake, throw the object across that lake, it'll go much further. And so if you keep imagining that eventually, if there's no friction, it will just keep going forever and ever without stopping, without slowing down, without accelerating. So we'll, in class, maybe talk about other situations that the first law applies to, but basically it introduces the new quantity that we call force. The second law is where the calculations come in. And let me write it mathematically first. I'm going to put the sum. So this Greek letter sigma just means the sum, add up all of the forces Now, this really is the net force, right? If you add up all the forces, that's what we mean by the net force. But that net force has to equal the mass times the acceleration. So this is the place where everything, all the forces get added up, all the math gets done. But maybe one thing you can see is a lot of times, if I know the forces, I can get the acceleration. And this is an important thing, because once I have the acceleration, we can do the stuff we've done previously. We can figure out where the object is, how fast it's going, using maybe our kinematic equations, or maybe the acceleration isn't constant. We got to do some other mathematical calculation to figure it out. But we can predict the motion once we know the acceleration. How do we get the acceleration? We add up the forces and set them equal to ma. Now this brings up another question. How do I know what the forces are? In chapters 5 and 6, we'll talk about various forces. Some problems will just say, hey, here's a force, here's another, add them, set them equal to ma. But as it turns out, we have to make a guess. We go out in nature and we observe, there's an acceleration. What is the force? Make up a formula for that force and see if it works, see if it gives the proper acceleration. So for example, the force due to gravity, when Isaac Newton first came up with these laws, he also came up with a formula to calculate the force of gravity between a planet and the sun, for example. And what he was able to do was to show that by adding up that force and setting it equal to ma, that he could then get the position and the velocity of that planet at any later time, right? And so based on sort of that observational evidence or experiment, we know how to calculate the gravitational force. And there are a lot of other forces in nature. Next term, we will talk about electrical forces, but we can always plug them in to Newton's second law. In chapters 5 and 6, you'll be given several forces. So we will talk about some of the forces that apply there as we go on. We'll do an example here at the end, and you'll hopefully see in better detail what I mean. But let me ask one last question here. Before I go to the third law, what are the units? Well, if you look, a force has to have units of kilograms mass times meters per second squared, right? Mass times acceleration. And this is called a Newton, or just capital N is the abbreviation. So the unit of force in the metric system, or the SI system, is the Newton. And it's equal to a mass times acceleration of kilograms meters per second squared. Okay. Now the third law, let's just get that down here. The third law is again based on experience. For example, if I push on something, it pushes back on me. And we call the two forces that are involved, the force I push with on the object and the object pushing on me, as an action-reaction pair. And these again are equal and opposite to one another. And they are, they're equal and opposite, but they never get added together, right? Because they act on different objects, right? If I push on the table, my force is on the table. The reaction force to that is the table pushing on me, right? So there's a force on the table and a force on me on different objects, and you never add usually those forces together. If I want to know what my acceleration is, I would add only the forces on me. If I want to know what the table's acceleration is, I only add up the forces on the table. We'll again come across a lot more examples or several other examples of this, but that's an important point to keep in mind. You never add the action-reaction pairs, right? Well, I shouldn't say never. It depends on what you're trying to do. But if you're looking at a particular object accelerating, you never add the forces that object is pushing on other things with. Okay, so that is just a quick list of Newton's laws. And we'll talk more about them as we go on. The main thing that I kind of wanted to do today is to do an example to show you how this works. And so I have an example problem. This problem actually comes from the book. I believe it's problem 5 in chapter 5. I've modified it a little bit here to make it kind of more like a context-rich problem. So as an intern working for NASA, you're asked to study the following situation. The 3 astronauts here are going to push on an asteroid to guide it toward a processing dock on a spacecraft. And the forces that they're pushing with are given. In order to safely intercept the spacecraft, right, we need to know what the asteroid is going to do. And we need to know the position and the velocity of the asteroid, maybe after a time of 10 seconds. Okay, and so, you know, I may not go through all the steps of the identify, set up, execute, evaluate, IC method here, because we have just barely introduced this, but I can write up a plan, right? So let's go and write up a plan or a setup, the second step. Now, I know that there are forces involved, and those forces are going to cause the asteroid to accelerate. And I know that in order to figure out the acceleration of that asteroid, I have to add up the forces and set them equal to ma. So first of all, I need to get the components of the vector, of the force vectors, add them, and solve for the acceleration. There's kind of 3 sub-steps, I guess, to that. But this is often, or almost always, what's going to happen when you are given forces. You will plug them into Newton's second law, and that means adding up them as vectors, right? Forces are vectors. They have a magnitude and a direction. Now, the second step, once I have the acceleration, I need to figure out what is the position and the velocity. So if I want the velocity, I can use kinematics. And the reason I can use kinematics is that the forces are all constant, so the acceleration is going to be constant. And I'm going to assume that the initial velocity is 0. Right? It doesn't say that in the problem, but I'm going to assume that. I wasn't told that it wasn't, so let's assume the initial velocity is 0. So I might find, if I want to find my final velocity, well, I have the initial plus AT. It's my kinematic equation for velocity. I can also use kinematics to try and find, again, assuming initial velocity is 0, the displacement or the position, right? What if I want to know the distance that it goes? Well, that would be VIT plus 1/2 AT squared. But again, we're assuming initial velocity is 0. Okay. So I'm going to use just my kinematic equations. So kind of several steps, adding the vector components, solving for A, then using kinematics is sort of my plan. So let's add up the forces. So looking back here, I've got this force 1 of 32 newtons at an angle θ1. So I've got an X component and a Y component. And my X component is going to be cosine θ1 times that 32 newtons, sine of 31. Maybe I'm not going to go through all of the steps. Again, I'm just using trigonometry to get the X and the Y components. I notice F3 does have a negative Y component. It's pointed downward. And F2 only has an X component, okay? So again, I'm just using the angles and the magnitudes of the forces, using trigonometry sines and cosines. And let me write out what I get for all 3 forces. So my first force, let's just write it out this way. I'm going to have 32 newtons cosine of 30 degrees I hat plus 32 newtons sine of 30. All right, just the X adjacent and opposite sides. F2 does not have a Y component. So it is, or sorry, yeah, it does not have a Y component. So it is just 55 newtons I hat. And then F3 is 41 newtons cosine of 60. I hat, and then it had the downward y component of minus 41 newtons sine of 60 j hat. All right, so writing these all out, let me just put the numbers in. F1 is 27.7 newtons I hat plus 16 newtons j hat. So now I'm just using the calculator to calculate these numbers. F2 is still, it's only 55 newtons I hat. And then F3 is the 20.5 newtons I hat, which is the 41 cosine of 60 minus 35.5 newtons j hat. All right, so now to get my net force, I just add these components together, right? So I add all the x components, I get 103.2 newtons I hat. And then I add the y components, I'm going to get negative 19.5 newtons j hat. That is my net force. Right? And so I've got my net force. The next step is to set it equal to mass times acceleration. So one way to, there are kind of a couple ways to do this. One way is just to work with the components and just find out, you know, how far has it gone in the x and how far has it gone in the y. The other way would be to figure out the magnitude and the angle and figure out how far has it gone in a straight line and at what direction, what angle. Let's start out just by doing the components separately, right? So whenever I write sum of the forces equals MA, what it means is that the x components equals MAX and the y components equal MAY, right? So in my x direction, I have a force of 103, that should be 103.2, I believe. 103.2 newtons, and that's equal to the mass of 120 kilograms times the acceleration x component. And remember, acceleration is a vector too. It can have an x and a y component as well. And so if I solve for AX, my x component of acceleration turns out to be 0.858. Just dividing 103.2 by 120. Now that's just the x component. Now the y component, I do exactly the same way. I just use the sum of the forces in the y direction, their y components, equals MAY. Again, the mass is 120 kilograms. This, let me just write it here. It's negative 19.5 newtons. So take that negative 19.5 divided by the 120 kilogram mass, and you get negative 0.163 meters per second squared. All right, so there are my x and y components. Right? And now what I can do is do kinematics. So let me go ahead and do this on the next page. Let me get a new slide. So what I've done is I've actually got my acceleration vector in terms of its components as 0.858 meters per second squared I hat minus 0.163 meters per second squared j hat. Now, what if I want the velocity vector at any time? Okay. Well, remember our kinematics, right? V final equals V initial plus AT. Well, this works for either component. So what I'm going to have is AX times T I hat plus AYT j hat. Now my A's are just these numbers. Right, and my time is going to be 10 seconds. So V at 10 seconds is just 0.858 times 10, 8.58 meters per second I hat, minus, well, it's going to be minus when I take this acceleration times 10, minus 1.63 meters per second squared j hat. And there's my velocity at 10 seconds. Okay. Now to get my distance or my, let's say it's my position vector really at 10 seconds or at any time, let's first of all just do it for any time. Instead of using axt, I use 1/2 axt squared, right? Again, b initial is 0 in either the x or the y direction. So I just use my x and y components. Plus 1/2 ayt squared for the y direction. Again, plugging in my acceleration of 0.858 and my 10 seconds squared here, I get 42.9 meters I hat minus 8.15 meters j hat. All right, so my position at 10 seconds, I have now calculated in terms of the x and the y components, right? So this is the x position and this is the y position. That's perfectly fine. But if you did want to get the actual distance, right? Well, you could use Pythagoras's theorem on this and calculate the actual magnitude of the position and calculate the angle. Now I'm going to do one as the last thing here. Let's look at a different way I could have done this. I could have gotten the magnitude and the direction of the force. It all depends on how I want to write my final answer. But to get the magnitude and direction of the force, right, well, what I have of the net force is it's kind of going like this. And let's see, we had a magnitude of 103.2 in the x direction. And then we had negative 19.5 going down in the y direction in newtons. So if you use Pythagoras's theorem, right, the magnitude of that net force is square root of 103.2 newtons squared plus 19.5 newtons squared. That comes out to be 105 newtons. Now this force is the combination of those two components, right? It's pushing down at an angle that we can now compute using the inverse tangent of the opposite side, 19.5 over 103.2, which turns out to be 10.7 degrees. So we know the size of the force, the magnitude, and the direction. Now, what if we wanted the velocity after 10 seconds? Well, okay, we would write velocity is equal to AT, but now we're using the magnitude, right? In fact, actually, first of all, before I can write velocity, I have to get acceleration. So let me talk about that first. To get the acceleration, right, we're going to take some of the forces over the mass. So it's just 105 newtons. Now this is just the magnitude. 105 newtons over 120 kilograms. So we get, let's see, I think it's 0.875. This is the magnitude of the acceleration because I've used the magnitude of the force. What is the direction of that acceleration vector? Well, it's in the same direction as the net force, right? The asteroid is being pushed down the same way, or the acceleration is the same way it's being pushed. So this is at 10 degrees, 10.7 degrees below the x-axis as well. Then to get our velocity at any time, just take a times t, right? Multiplying by 10 seconds, we'll get 8.75 meters per second squared. Again, the direction, right, is the same as the force and the acceleration. It's at 10.7 degrees. What about our distance? Well, use 1/2 AT squared. If you do that, you should get, well, I didn't actually calculate it, it looks like. But you will end up getting the distance at 10 seconds, right? If I just take my 8.75 meters per second squared times my 10 seconds squared, plug in the numbers, whatever you get, whatever number you get is the distance it actually went along a straight line at 10.7 degrees below the x-axis. So it's all in the same direction, but I'm now dealing with the magnitudes. So my position vector would be this distance in a direction of 10.7 degrees below the x-axis, right? So there are two ways. I can just deal with the components by themselves, or I can deal with the magnitude of everything and then talk about the angle. Most of the problems we will do, we will use the components, right? It's just easier to deal with the x and y components because they're independent. Now, if I wanted, though, to go from this component method to the magnitude, it's easy, right? I just take, if I want the magnitude of the velocity, I just take this squared plus this squared and square root, right? They are just new vectors, a velocity vector, a position vector with different sides or different components. Now, it'll turn out if you calculate the angle for all of them, it's always going to be 10.7 degrees below the x-axis. So that's an example, and I really wanted to emphasize that you're always adding up vectors. And to add vectors, you can always use the x and y components separately. Right? So hopefully that will help with at least one or two of the problems. And I'm going to stop there. We'll talk more about forces as we go along further in chapters 5 and chapter 6.